Complexity is all around us, in both the natural world and in our engineered world. Although we can't take credit for complexity in nature, in recent decades, humans have outdone themselves in the engineered world. If we look at the history of every item created and made by human hands, a clearer pattern begins to emerge. Often those items start off in a simple form, and generally over time they become more complex, safer, and more efficient than the previous iteration. This can be seen time and time again in everything from the smallest items like computer chips, for example, all the way up to the vast array of infrastructure that support our largest cities. The engineering and critical thought that humans have developed and put into basic and complex items alike has continued to improve life as we know it. It's safe to say that as humans move around, working and living day to day, that most people take these items and the systems for granted and have adapted to our multifaceted world, expecting speed and efficiency in everything, from apps on our phones to computers and 5G connectivity on every corner. Attempting to understand the complexity and engineering these items provide humanity is overwhelming, and the truth is people want things to just work. In fact, in most organizations, there is an expectation and a continual drive to improve systems to run faster and more effectively every day. One example of a system that started off small but has grown to be one of the most complex systems of today is the National Airspace System, or NAS. Every day, more than 44,000 flights safely take off and land here in the U.S., totaling more than 16 million flights per year. In fact, close to 15,000 air traffic controllers, 4,500 aviation safety inspectors, and 5,800 technicians operate and maintain services for our national airspace system. It has more than 19,000 airports and 600 air traffic control facilities. In all, there are 41,000 NAS operational facilities and over 71,000 pieces of equipment, ranging from radar systems to communication relay stations. Even with all this infrastructure, the process is seamless to most of us on the outside due to the dedication of millions of professionals who work on the inside to provide safe flights in and out of the national airspace. And while this elaborate system works seamlessly for the most part, great care must be taken when new advancements are engineered into it. Just looking at the raw numbers, it's easy to see that the National Airspace System is an elaborate, intricate, interconnected system. As just illustrated, there are many different moving parts, but not surprisingly, the major choke points within the NAS are the airports themselves. They are incredibly multifaceted, with countless moving parts, such as personnel, hardware, software, and air traffic control, just to name a few. Integrating new systems that will ease the complexity at the airports while maintaining the same standard of safety and convenience is a huge undertaking. This integration needs to be seamless, keeping the flying public safe while also allowing new systems to perform their assigned tasks. In recent years, NASA, the FAA, and industry partners have been working on a new system called the Airspace Technology Demonstration 2, or ATD-2, that is designed to streamline certain operations at the airports to make the entire system run more efficiently. Primarily, the team is working to integrate Arrival Departure Surface, or IADS, at airports, with the stated goal to improve the predictability and the operational efficiency of the air traffic system in Metroplex environments. On this episode of NASA X, we will look at this ATD-2 system that was tested and validated over a number of years in some of the busiest airports in the country. And now that the testing phase is over, we will also learn how this new system could drastically reduce delays while maintaining the same level of safety for the flying public. Whether you fly often or infrequently, your flight can often be delayed. There are many reasons for delays, such as weather or maintenance on an aircraft. Very often, communication across the NAS, hindered by aging technology, is the culprit. Without shared information across all airport operations, a lack of predictability of aircraft movement can lead to overall system inadequacy, which can cause delays, greater fuel burn and emissions, and just overall headaches. Knowing that these inefficiencies needed to be addressed, the ATD-2 effort was established to help solve many of these problems and make the airport environment operate smoother.
The ATD-2 team leveraged what we refer to as an agile software development process. So what this really means is, instead of waiting and creating a perfect product that has all the bells and whistles and rolling it out at the end, we took an incremental approach. So this means developing prototype software that might not have been perfect, but had some key features that we wanted feedback from our core users. This includes air traffic controllers, ramp operators, and all the various users that actually would be utilizing the system on a daily basis. So we developed what we refer to as a series of shadow sessions, in which we brought together users from all these disparate groups and had a conversation. In this conversation, we not only asked them for feedback on the software that we were developing and the manner in which these algorithms functioned, but also gleaned insights from these operational users who had decades of experience that we were able to take and implement in a tool. This was a key component of developing a system that not only the users were able to utilize on a daily basis, but also ensure that it depicted the information they were truly interested in seeing.
Like many scientific investigations, ATD-2 was run in phases. The first phase demonstrated what is called tactical surface departure metering at American Airlines Ramp Tower and FAA's Air Traffic Control Tower at Charlotte Douglas International Airport, as well as overhead stream insertion at Washington Air Route Traffic Control Center. The next phase extended the surface departure metering time horizon with strategic planning tools, interfaces with tower controller electronic flight strips, and expanded overhead stream insertion to Atlanta Air Route Traffic Control Center. The final phase demonstrated a terminal departure scheduling capability over multiple airports. The first phase, beginning in late 2017, started with a single airport, before moving to multiple airport settings. After looking at several options, Charlotte Douglas International Airport in Charlotte, North Carolina, was chosen to conduct initial testing. Charlotte was ideal for many reasons.
It turned out when the FAA and NASA were looking for a location to demo this technology they were developing, Charlotte turned out to be an ideal location, primarily because of where we're located along the East Coast and the multiple centers that we deal with. We have a very difficult time getting aircraft off the Charlotte airport into the overhead streams. And we have 9 very definite arrival and departure banks a day at Charlotte with about 45 minutes of recovery time between each of them. You could not have tested a technology such as this at an airport like Newark, LaGuardia, or JFK. You run the risk of grinding the whole system to a halt. So Charlotte was an ideal location to roll this out, and eventually this technology, after it's incorporated into TFDM, will be rolled out to all those other busy airports. Anybody who takes a look at the Charlotte Douglas International Airport and sees a map of it sees the runways of a major international airport. If they look closely, however, they'll see that we have the ramp space of a mid-sized regional airport. And our departure and arrival banks at Charlotte pretty much overlap 9 times a day. And we move between 75 to 80 arrivals and 75 to 80 departures through a very small confined ramp space at Charlotte. We can't build our way out of this one. To find the inefficiencies that are there and to make things more efficient, we're going to have to use technology. And once we begin using this technology and are sharing the information that we have, and the airlines are sharing the information they have with us, we should both be able to come to a much better solution to this problem and become more efficient.
What the FAA does is it tries to manage the flow of aircraft through the airspace so that the carriers, Uniteds, the Americans can provide you the opportunity to fly from where you live to where you want to go. The FAA tries to do that in the most cost-effective and efficient way because there's demand grows. We need to try to keep that a cost-effective solution and a reasonable solution for you as a passenger. The last thing you want to do is spend hours in airports waiting for your next flight. What NASA does is build the technologies that allow us to meet that need. So they provide tools that help us move aircraft efficiently into airports, through airports, and out of airports. We're really grateful for that work. The tools they build help make the flights more fuel efficient, more on time, which reduces the cost for the airlines, and make it an easy, enjoyable visit to wherever you want to go.
We're very excited about this partnership in Charlotte especially, and we have not only American Airlines involved with NASA, but the local FAA folks are involved, the airport authorities involved. It's a real true collaboration. The airport surface for many, many years has been sort of the black hole in terms of understanding what's happening on the surface and how that connects to the overhead stream of aircraft. So what we want to do is be able to give the traveling public, whether it's American Airlines or other carriers, a more predictable experience, because there's still a lot of uncertainty today when you push away from the gate and you wait to take off, and I think we've all been through that at one time or the other.
As previously mentioned, NASA's ATD-2 IAD system improves the efficiency of surface operations at the nation's busiest airports through time-based metering of departures and improved sharing of flight operations information amongst the various airport surface stakeholders.
In the single airport IAD system, such as the one that's deployed at Charlotte Douglas International Airport, the benefits come from mainly two mechanisms. The first is surface metering, and the other one is overhead stream insertion. For surface metering, you consider an aircraft that's waiting in the departure queue for its turn. If instead of being stuck in the departure queue, if this aircraft is able to reserve a spot in the queue, then it won't have to push back from its parking gate and be idling in the departure queue. This is very similar to the restaurant reservation system, where you book a table based on your schedule, then you just show up at the right time and skip the whole wait. This is exactly what the ATD-2 surface metering is. The other mechanism for single airport benefits is the overhead stream insertion. And for this, you consider controlled flights which have a constraint on their departure time. The ATD-2 system is constantly evaluating the data and accessing the data to find the optimal pushback time for this flight so that it spends minimum time taxiing and still be able to meet its constraint.
So the ATD-2 systems, both the single airport in Charlotte and the multi-airport in North Texas, are all focused on delay savings, reducing delay, time spent with the engines running. We're able, though, to turn those time-based benefits into environmental benefits by computing engine fuel burn rates, and so we can identify how much fuel is saved by the system, and in turn how much carbon, CO2 emissions are saved, because there's a direct correlation between fuel burn and CO2. So the 3-year demonstration at Charlotte recently passed over 1 million gallons saved, which we're really happy about. And then we expressed the CO2 savings in terms of urban trees planted, equivalent urban trees, and the number there is 159,000, which is a really gratifying number. It's very nice to see the environmental benefits that these time-based delay savings can produce.
The final phase demonstrates a terminal departure scheduling capability that considers multiple airports and terminal boundary constraints. This third phase of the ATD-2 research was located in North Texas, with good access to several key facilities, including Dallas-Fort Worth International Airport and Dallas-Love Field airports, the Dallas-Fort Worth Terminal Radar Approach Control, Fort Worth Air Route Traffic Control Center, Dallas-Fort Worth and Dallas-Love Field Air Traffic Control Towers, and more importantly, close to the headquarters of American and Southwest Airlines facilities. Being close to so many facilities and multiple airports was key in ATD-2's effort to provide solutions for several problems in the complicated multi-airport environment. At most airports today, departures are managed in the order they push back from the gate, which can overload runways and cause excessive taxi and hold times. Additionally, significant uncertainty in the duration of the taxi out, takeoff, and climb phases of flight leads to inaccurate demand predictions, decreased situational awareness, and overly conservative airspace restrictions. ATD-2 departure metering recommends holding some departing flights a little longer at the gate, instead of having them wait in long departure queues at the end of the runway. Shifting some of the departure wait time from the taxiway to the gate saves fuel, reduces emissions, and gives airlines and passengers more flexibility in the period prior to pushback. The ATD2 IAD system also couples a trajectory-based surface decision support tool, similar to TFDM, with the overhead stream insertion capabilities of the TBFM en route metering decision support system. The result is a more precise scheduling of surface departures into constrained overhead flows, better communication between the en route and tower controllers, and significant improvement in compliance with target takeoff times at Charlotte Douglas International Airport.
The part of Phase 3 that is significantly different from Phase 2 is the multi-airport environment. So here in North Texas, we have two major hub airports, DFW with American Airlines, Dallas Love with Southwest Airlines. So what the objective is, again, is to identify areas, whether they be on the surface or in the airspace, integrate that information into one product, provide flight operators and ATC information on, this particular route may be congested, and based on the data that the airlines have provided that we have integrated into the system, identify flights to them that may benefit from a reroute. Most often that's delay reduction. Sometimes it can be a reduced number of flying miles.
It really is a huge change because, one, it's never been done before. So in the past, what would happen is that we'd file our route, several hours prior to departure. And obviously things can change, and as when we file our flight plan, we're not always aware of what everybody else in the airspace is filing, nor are we really aware of all the constraints that are emerging that might make our path suboptimal or inefficient. So what ATD2 is allowing us to do is to react to those changing conditions and to continually optimize our routes up until the point of when we take off. And so that requires significant coordination between the airlines and ATC, but it also requires significant computational capabilities to say, evaluate my current route, given the current conditions, and evaluate all the options that might exist to mitigate those.
Much of the inefficiency in today's air transportation system can be attributed to a lack of information sharing amongst the operators responsible for managing air traffic in busy terminal environments. Concepts and technologies to improve the handling of arrival, departure, and airport surface traffic have been under development by NASA, the Federal Aviation Administration, and industry. But to date, these capabilities have largely been developed and implemented independently. NASA's investigation into the needs of air transportation stakeholders, including airlines, air traffic service providers, airport authorities, and technology vendors, revealed that an integrative approach is needed to address this inefficiency. With this innovative approach, the airline operators are seeing great benefits.
The way I like to describe it is to really explain it, it's almost like Waze for the sky. And while that will fall short as an analogy, it helps to illustrate. I use Waze every day when I drive to work. And I use it every day because every day is different. Every day the situation changes, whether it's road closures or traffic or bottlenecks. And so it helps you kind of navigate that road every day. And it helps me to say, if I stay on my normal route, this is how long it's going to take. And it actually gives me options to say, if you want to avoid some of those bottlenecks, try this way. And it'll give me kind of an estimate of what that would take. And sometimes I can avoid those bottlenecks altogether. Sometimes it just allows me to mitigate some of those. And that's exactly what ATD2 Phase 3 is doing. It's saying for me as an operator, hey, every day is different. And sometimes the airspace will have different constraints in it. And if you stay on your filed route, this is what's going to be the outcome that in terms of delay or ETA. However, if you want to change to an alternative route, much like Waze can redirect you, this is how much you would save, or this would be the way that you can mitigate some of those obstacles. And really, so it does that, but it actually takes that one step further because it allows us to actually implement it with the FAA.
It helps to achieve delay reductions, by looking at the airspace, but it also brings a lot of additional data that we don't have today. For example, the timeline is really something that has been extremely beneficial. You understand what's going on the ground. You understand, will the MOT potential issue be a real issue or not? Do you have to call, the tower to ask for expedite traffic? So that has been extremely useful for the ATC coordinator. So as we talk about that, it's also a tool which really helps situational awareness.
Before, we would get off the gate and we'd sit there and wait for something to open up, or if a controller was able to push us off onto another gate, we could be out there an hour. Now, with ATD2, we can find out what our restriction or what our departure time would be 45 minutes to an hour in advance, and we can plan for that. So once we get off the gate, we can get it to a better departure gate and get airborne a lot quicker. The benefits are we can get in early to some of the cities we're flying to. We're able to save a lot of money and time by saving those delays, saving fuel, and we're not sitting out, burning gas on the runway, creating all sorts of noise and pollution. We can just get airborne right away and get passengers or customers where they need to be a lot sooner.
Not only is ATD2 helping the airline operators, but it is also helping reduce the workload of the air traffic controllers.
So during my career, I have seen many programs and systems strive to increase efficiency. That's what most of these new projects try to do. In my opinion, what all the successful ones have in common is automation or procedures that help reduce controller workload and increasing the efficiency at the same time. Reducing controller workload is normally not the primary goal of most of these projects, but it definitely ends up being a result. So by reducing the controller workload, we can increase efficiency, increase capacity in the NAS, and then that'll translate into savings for the flight operators.
As the work from this team begins to wrap up, what they have accomplished has drastically changed the way the affected airports do their jobs for the better. But will this technology move from the test sites to a nationwide deployment?
The single airport technologies that we're demonstrating in Charlotte are on a path to deployment by the FAA to 27 airports across the nation. And the FAA has told us that our demonstration in Charlotte has exceeded the benefits that they projected for the system. So they're very pleased that, to have these demonstrated benefits to talk about as they take the system into nationwide deployment.
This demonstration is more than a success story. It is a story in the making. Imagine the possibilities when the FAA deploys NASA technology at airports across the country. Through this demonstration, NASA once again proves its value to our nation, building on decades-long problem-solving of the nation's toughest challenges. This can-do agency will continue to make history in air travel for generations to come.